Okay, class, we're continuing our video lectures on the Earth and planets. It's kind of a little warm up here. I think I'll try to move a little further away from the sun. So in this video lecture, we're gonna talk about the nebular hypothesis. That is the hypothesis of how the solar system was formed. As we talked about in our last video lecture, data shows that the solar system was formed about 4.5 to 4.6 billion years ago. And we'll talk about in this lecture about how it formed as a result of gravitational collapse of a giant cloud of gas and dust. Just as an aside, also mentioned the solar system is located in the Milky Way galaxy and what is called the Orion arm of the Milky Way galaxy. That Orion arm is about 26,000 light years from the center of our own galaxy. Again, to give you some idea of the distances we're talking about, that is, would take a light 26,000 years to travel from the center of our own Milky Way galaxy to us here on planet Earth or to our sun. Tremendous distances. Well, let's first talk about this so-called nebular hypothesis, which is pretty much agreed upon by people in planetary sciences as being a good model. So let's say that 4.5 to 4.6 million years ago, there was a cloud of gas and dust, what is called a nebulae, and it began to collapse. That would be the upper left of our drawing here. That it began to collapse due to gravity, and as it collapsed, things got hotter. As you can see, it's sort of glowing red, and things began to spin, forming a flattened disk as we go from the second to the third drawing. And the lighter gases, helium and hydrogen, which are the predominant elements that make up the universe, but hydrogen and helium coalesced or collapsed towards the center, forming a very hot core, which became the sun and became so hot that it supported nuclear fusion, which further released energy in sunlight. And it's why we get our heat and light from the sun, because of the nuclear fusion reactions taking place on the sun. But then further out from the center, matter clumped together in various sort of rings or at various distances from the center, and eventually coalesced to form what are called planetesimals, essentially big chunks of matter. The planetesimals collapse via gravity to form planets at these various distances from the center. The denser materials forming the terrestrial planets near the center of the rotating disk, and the lighter materials sort of moving out towards the far reaches of this spinning disk, forming the gas giant planets. Now, as the planets would spin around in these orbits, each of the forming planets would clear a path. That is, due to gravity, if a big chunk of matter is revolving around the center of this rotating disk, anything that is near it or in front of it or behind it would be pulled by gravity to that larger chunk, so that eventually it would sort of accumulate like a snowball rolling downhill. It would pick up all of the debris to form bigger and bigger planets. So each planet cleared a path of nearby smaller objects, and because of gravity, those planets would become spherical in shape. Okay, so that is what is called the nebular hypothesis, and at the bottom left of this drawing, you see little images of what you could recognize as the planets in our current solar system. Now, each of these planets orbits or revolves around the sun in a nearly circular path. Now, they're not exactly circular, but they're nearly circular paths, and they're all in the same plane. And remember, in that nebular hypothesis, it would sort of be like a flattened pancake, a revolving pancake or dish. So the planets are all in the same plane, more or less. Some of them are a little bit off, but more or less, or they revolve around the sun in the same direction. That direction is actually counterclockwise if you look from the the north of planet Earth, which would also be the north of the sun, if we describe the sun as having a north and a south pole, because the sun is actually also rotating itself. And each planet also rotates around an axis. It's spinning like little tops. And you would imagine that they would all be with the north and south pole pointing perpendicular to the entire plane of the solar system, but they're a little bit off kilter. As you may know, the Earth has a tilt of 23 degrees, 23.26 degrees. The other planets also tend to have a tilt of 10, 20 degrees. Uranus is an oddball here because it's really kind of off kilter. It kind of got lopsided, and I'm not quite sure why. Maybe it had a collision at some point in its lifetime, but most of them spin in a way that makes some sense. So the planets revolve around the sun. They have this long path revolving around the sun, and each planet itself will rotate on its own axis. The revolving around the sun, that period we call a year. For us, it takes, on planet Earth, 365 days for one complete revolution around the sun. And the rotation on the axis we call a day. And that, of course, takes 24 hours, what we call 24 hours in our days. Well, the other planets also have their day and year. And if we give them in terms of Earth days and Earth years, just as we did for the distance, the astronomical unit, and the relative masses and radii planets. If we refer to everything relative to planet Earth, we see some interesting patterns. For the 4 terrestrial planets, we have revolution periods of 88 to 687 days, but reasonable. But then when we get to the gas giants, Jupiter, Saturn, Uranus, Neptune, we're talking about many, many years. Instead of 1 year for planet Earth, it takes about 12 years for Jupiter to revolve around the sun, about 30 years for Saturn, 83.8 years for Uranus, and 164 years for Neptune to make its way all the way around the sun. That may be reasonable because as Saturn, Uranus, Neptune are further away, it would just take them longer to travel the complete arc to go around the sun. But also what's interesting is the period for rotation, the day for each planet. And that can be quite interesting. Whereas on planet Earth, we rotate in 24 hours, 1 day. Mercury, which is smaller and you might think would rotate more rapidly, it takes 59 days, almost 60 days to rotate around its axis. Venus, also very slow in rotating, 244 of our days for it to make one rotation around its axis. But yet the larger planets, the gas planets, seem to rotate more rapidly. Jupiter, about 10 hours, Saturn about 10 hours, and Uranus and Neptune about 16 hours to rotate. Now, one way you can think about this is that because they're mostly gas, they can rotate more rapidly, but that still is very, very rapid rotation of that entire massive body. Even if it's gas, it's large. To go a complete turn, it's very, very rapidly. They're very, very rapidly rotating, and that may be one of the reasons why we talk about these storms that occur on the surface of Jupiter, because everything is moving so rapidly. Another interesting feature, look particularly at Venus. It takes 224.7 of our days to make one revolution around the sun, but it takes longer for it to rotate around its axis. So what this means is that if imagine my cup here is our planet Venus, as it's going around, it has almost the same period of revolution as it has period of rotation. So as it goes around and one side of the cup is facing the sun, it will go around and trick of magic. When it comes back, you're going to have essentially the same face of Venus facing the sun, because it rotates on its own axis so slowly compared to how compared to the length of time it takes to revolve around the sun. So you would imagine that if there were any life forms, which there are not on Venus, those on one side would get a lot more sun than those on the other side of Venus. Another interesting thing, again, because I'm a chemist, I suppose I find this interesting, is the elemental composition of our solar system. If you look at the blue line, or the blue circles, this is the elemental composition of the entire solar system, counting the sun and all of the planets. And this information can be obtained by various types of spectroscopy. You see that we have a lot of hydrogen and helium. That's the first two dots at the top of this graph. And then there's a very small amount of the three next elements, which are lithium and beryllium and boron. Very small amounts. But then it jumps back up and we have a larger amount of carbon and nitrogen and oxygen, which are the next three dots: carbon, nitrogen, and oxygen. Now that's kind of interesting because carbon, nitrogen, and oxygen are essential for life. So we're fortunate that there's a relatively large amount of those elements in our solar system and on planet Earth. But also most of the elements in our solar system and in the universe, for that matter, are hydrogen and helium. Now, note that the axis that we're showing here are powers of 10. So there will be approximately 10 times as much hydrogen as there is helium. As we drop down, that's like 1, 2, 3, 4, 5, 6, 7, 8, almost 10 to the 8th times less lithium in our solar system as helium. So again, these are powers of 10. So there's a much, much less of these elements and a reasonable amount of carbon, nitrogen, and oxygen in our solar system. Now, the black dots are for what are called galactic cosmic radiation. That is, from that radiation, we can get information about the elemental composition of the rest of the universe. And you can see that we follow the trend more or less, but we do seem to have less of some elements in our solar system and on planet Earth. Also, a relatively large amount, kind of a spike for iron, and a little bit more maybe silicon than you might have otherwise guessed in our solar system and on planet Earth. Silicon, sand, iron is at the core of our planet. Okay, we're going to again pause and have a little quiz and then continue on. And in the next video lecture, we'll talk about the Earth and our moon, our beloved moon. Never